first year of high school at Florida Atlantic University High School in the United States. I'm also the software lead for their University CubeSat team over at FAU, and I'm a member of the Wolfpack CubeSat Development Team, which is how I got my start in aerospace. I'm here today with my colleague in the Wolfpack, Karsten, and I'll let him introduce himself.
Hello, my name is Karsten McCalla-Bottorff. I'm going into the 7th grade at the Green School, which is in Florida, America. This is my first time speaking at an international conference, and I'm also a new member of our organization, the Wolfpack.
So the Wolfpack CubeSat Development Team is a group of middle to high school students that are dedicated to designing, building, testing, and launching CubeSats. We also present our research at international conferences like COSPAR, and we advocate on behalf of the aerospace industry at state and national legislature in the United States. But most importantly, we've been around for almost a decade, and we've launched 2 CubeSats in the past, with one actually due to launch fairly soon. Our first CubeSat, the WolfSat-1, was validated a lab-on-a-chip payload with extremophile bacteria. We launched it in 2018, and it was actually the first ever middle school CubeSat. Our second CubeSat, the CubeSat-1, launched in 2022 and validated a new type of capacitor technology as an alternative to lithium-ion batteries. This one was actually entirely proposed and built by middle to high school students, and was one of only 16 selected for the 10th round of CSLI in the United States by NASA. Our most recent CubeSat, the FlipSat-1, is a half-U that is set to launch. Was actually set to launch today, but we had a delay at SpaceX, so it will be launching soon. It is testing various kinds of radiation hardening technologies, and in order to prevent single event upsets in space. And it's also giving flight heritage to a new kind of processor, the microbit, a small computer that is meant to help children learn to program.
So the WolfSat-1 is a 10 centimeter by 10 centimeter by 10 centimeter cube satellite named after our organization, the Wolfpack. Its mission is to assess the impact of microgravity on Ideonella Sakaiensis' ability to digest polyethylene terephthalate, which is a common single-use plastic. This could contribute to the success of longer space missions and expanding our domain due to this recycling system that's easy and clean. We could also find an issue for a recycling system here on Earth. This is a self-funded mission that, as well with help from the Stiles and Nicholas Foundation, which said they would match the money we made from May to June, which ended up being $50,000. We were also fortunate enough to be selected as one of the 3 organizations by the Firefly organization nationwide in America to have a free ride to space. Our plastic pollution problem has been rising since the 1950s. Since the 1970s, plastic production per year revolution. In 2015, plastic production per year was more than 350 million tons. Due to our world recycling rates of lower than 20%, most of this ends up contributing to greenhouse gas emissions, which indefinitely leads to climate change. If we want to prevent similar issues from happening while we're exploring different domains, then we need to come up with a solution. And our proposed one is Ideonella Sakaiensis, which is a rare bacteria that has the ability to degrade polyethylene terephthalate. It uses 2 enzymes to do this, PETase and MHETase. The PETase cuts this polyethylene terephthalate into tiny pieces, which are called monoterephthalate, bis-TPA, and terephthalate. The MHETase takes this monoterephthalate and converts it into ethylene glycol, which creates a clean way to upcycle back into plastic. The bis-TPA and terephthalate, on the other hand, can be digested by any other microorganism. According to Louisiana State University, digestion is 20 to 30% faster while in a microgravity environment, meaning that we can have a potentially faster way to degrade one of our biggest issues. There are other possible microbes found to degrade plastic. One of them is Pseudomonas butida, which is found in soil, taking the rhizosphere, fresh and salt water, and on living surfaces of foliage and even on beaches. It converts this polyethylene terephthalate into beta-lactic acid for recycling, although it's not as clean. A second option would be for green nitrogens, which is bioengineered with the PETase genes from Ideonella Sakaiensis, combined with a bacteria that has quicker production and viability in a saltwater habitat. Due to it being engineered, it can operate in ambient temperatures. Instead of taking all of the plastic and microplastic that we cannot reach while in saltwater, we can use this bacteria to get to all of it. We simply chose Ideonella Sakaiensis because it is more efficient, as well as the ability to recycle plastic that is extremely rare.
Thank you. So just a little bit more about our satellite. Our payload will be as follows. It will be enclosed in a polycarbonate box measuring 6.35 by 6.35 by 3.81 centimeters. And inside the box will be a PET film, an LED, a photoresistor, and below our microcontroller. Up here you can see some CAD drawings of our payload and payload mounted on a CubeSat and the payload exploded, so you can see all of the hardware. So here's a notional, operational, preliminary CAD drawing for our payload. There will be an LED above the PET film with the photoresistor below it, and as the Ideonella Sakaiensis degrades the PET film, more light will be able to pass through, and the photoresistor will read this change, and the confirmation light will be lit up. So here's a preliminary concept of operations. About 30 to 45 minutes after deployment, a heartbeat will be sent to the ground. Then both experiments will begin. For our first experiment, the media will be pumped into the container with the bacteria, and the apparatus will be allowed to stabilize. From there, all the sensors and LEDs will be enabled, and data will be periodically collected as nutrients are pumped. For our second experiment, the PETase will be pumped directly with the substrate into the wafer, and blue LED will be used. The blue LED will shine, and as the substrate breaks down, it will fluoresce green, and this green light will be recorded by the photoresistor. For our bus, we will be using Near Space Launch's Fast Bus. It is an off-the-shelf bus purchased from NSL. It has previous low Earth orbit flight heritage and a technical readiness level of 9. In fact, we actually used this bus on our previous two CubeSat missions. So it's a 1U bus unit weighing 0.7 kilograms. For the power system, it uses maximum power point tracking solar panels, along with 6 power banks with a total of 16.3 watt-hours of capacity. It has an anodized aluminum chassis with mount points and an inhibit switch, and with a built-in flight processor. And for our radio, we will be using the NSL iStar S4 Iridium radio. So all information will be uplinked to the Iridium constellation and then sent down to the ground. And through the internet, we will access it through a console, so we have 24/7 data connection. It operates on the high end of the L band at 1.622 gigahertz, or 1,622 megahertz, and it is an omnidirectional radio. I believe that data range is less than 13.5 bytes per second, and each packet has 17 bytes, and it's sent 3 times to ensure it arrives. So here's just our software layout. For our microcontroller, we'll be using the Arduino Nano. The Arduino is responsible for reanimating the bacteria and pumping nutrients with the micropump. It must also regulate temperature with thermistor and resistor in order to ensure the bacteria's survival and the enzyme's efficiency. And it must collect data with the photoresistor and downlink this data to the ground. And if the NSL fast bus enters modes 8 or 9, it has to suspend payload operations until we can regain power. So, as we mentioned before, ground studies cannot adequately mimic the low Earth orbit environment, specifically microgravity. And especially for future planetary sustainability, we need to be able to understand how plastic degradation functions in the microgravity environment. Especially for long-term space missions, it's crucial to be able to recycle these resources, especially in order to conserve resources and turn these plastics into more basic building block materials that we can repurpose for other things. Kind of like a composter, but for inorganic materials. This research is crucial for future planetary sustainability efforts, both in space and on the ground. So this also has the added benefit because CubeSats are a very cheap way to do research in low Earth orbit, and they can be done on a relatively short time frame, which makes space more accessible for pre-college education, and in the process gives us students a very valuable STEM experience. We get to see how these various STEM fields interact with one another, like mechanical engineering, software engineering, even biology, some aspects. And we get to it helps us form our STEM identities so we can be more sure of what we want to study as we enter the industry later on. We also get a lot of real-world STEM experience, which is also very helpful as we move up into higher education and into the industry. So just to wrap things up, our mission will be launching in the end of 2025. At this point, I want to thank everyone for your time and for your attention, and if there's any time, well, we'll be happy to answer any questions.